Alrighty, good afternoon. I think it's still good morning. Today, we are going to continue talking about graphs and derivatives. Specifically, I want to finish section 4.4 on L'Hopital's rule. And I want to give you a little preview of section 4.5 if we can get there. 4.5 tends to be a slightly challenging section because it calls back on a lot of graphing skills from pre-calculus. And then it asks us to kind of infuse those with the stuff we've learned in sections 4.3 and 4.4 on how the derivative affects the shape of the graph and how L'Hopital's rule can be used to investigate values of functions near weird points. Certainly also useful for finding horizontal asymptotes. So we'll cover all of that today. And that way next Monday we will be ready to dive into 4.5 in earnest. Last time we talked about indeterminate forms. I showed you what an indeterminate form is, and we saw how to use L'Hopital's rule to evaluate limits that yield indeterminate forms when they're either a ratio, like 0 over 0 or infinity over infinity. And we saw one example of an indeterminate product, something like 0 times infinity. Today I'm going to look at some more indeterminate forms. Maybe a couple more indeterminate products, some indeterminate differences, and then we're going to tackle what is probably the most challenging part of section 4.4, which is the indeterminate powers. So let's do the thing. This is MAC2311 section OH1, which is Calc 1 honors. And today is the 22nd of October, 2021. So like I said, today we're going to finish 4.4 on indeterminate forms. And L'Hopital's rule. And then I might introduce a little bit section 4.5 on curve sketching. So let me begin by saying, recall the following expressions are indeterminate forms. Certainly 0 over 0 and infinity over infinity. Also 0 times infinity or infinity minus infinity. 1 to the infinity, 0 to the 0. And I always forget this. Is it 0 to the infinity? It's our last indeterminate form here. Just for whatever reason, you know it when you see it. Is it 0 to the infinity? Infinity to the 0. Yeah. So each of these things are indeterminate because they're kind of made up of two pieces which are fighting each other. Right? If the top of the fraction wants to go to 0, that wants to make the whole thing 0. And if the bottom of the fraction wants to go to 0, that wants to make the whole thing infinite. So kind of this guy is trying to take you to 0, this guy is trying to take you to infinity. The opposite is true here. If the top is getting big, that wants to make the whole fraction big. If the bottom is getting big, that wants to make the whole fraction small. So these are objects that are fighting each other. In that same way, if something is going to 0 and you're multiplying by something going to infinity, this wants to drag you down, this wants to build you up. Infinity minus infinity, same thing. This wants to be big, but this wants to make you small again. The powers are more interesting. If a base is going to 1, that wants to make the whole expression 1. But if the power is getting enormous, you can take something that's very close to 1 and raise it to a large power and get something big out. 0 to the 0, same issue. The 0 down here wants to make the whole expression 0, because 0 raised to any power should be 0. the 0 up here wants to make the whole expression equal to 1, because anything raised to the 0 should be 1. And then same sort of thing here. If the base is getting big, that makes the whole thing big. But if the power is going to 0, that makes the whole thing 1. So these are all in conflict with each other, and that's what makes them indeterminate forms. Remember, the first two are called indeterminate ratios. And an indeterminate ratio is the only thing we can apply L'Hopital's rule to. 0 times infinity, this is an indeterminate product. Infinity minus infinity is an indeterminate difference. And these three are called indeterminate powers. And what we do when we encounter one of these depends on which type of thing it is. So indeterminate ratios, we can use L'Hopital's rule on. But all of these need to be turned into indeterminate ratios before you can apply L'Hopital's rule. Now, I think the homework set I gave you, you only had indeterminate ratios. So I am going to open up an extra little homework set for you today, where you've got some indeterminate products, differences, and powers to work with as well. I'll probably have that new homework set be due for you next Wednesday or something, so you can work it over the weekend, but if you don't get it done over the weekend, you can work on it Monday and Tuesday also. But I don't want to push these to next week because they are a part of 4.4. I guess the other option would be to just add them to the 4.4 homework, but that's due on Monday. I think that'd be a little cruel. So we'll have a little extra half homework set just for these. Okay. Let me grab one more example of an indeterminate product for us to play with. We can make it up like that. Let me grab stuff here. This is good. Yeah. Oh no, that's a little boring. We've done that. Something more challenging would be fun. That's okay. 43 is all right. So for example, let's try to calculate the limit as x goes to infinity of x times the sine of pi over x. So to get started here, we want to figure out just what's going on. What kind is this an indeterminate form? Right? If not, then we don't need any of this stuff. If it is an indeterminate form, what kind of indeterminate form is it? So what I would say at the start here is if we just plug in infinity, this looks like infinity times the sine of pi over infinity. Now, what is pi over infinity?
Is that 0?
It is, yeah. Any constant divided by infinity is 0. And the sine of 0 is 0. So this is infinity times 0, which is an indeterminate product. And we saw one of these problems on Wednesday. Who remembers how we handle an indeterminate product?
Is there some kind of rearranging to turn it into a ratio?
Yeah,
I don't remember
exactly
what the rearranging was.
So we've got two choices. Like Sarah said, we're going to need to turn this into an indeterminate ratio. So I'm going to do some algebra with x times sine of pi over x. And there's two ways to turn this into a ratio. I can either shove the x downstairs, which will make it 1 over x, or I could shove the sine of pi over x downstairs, which would make it 1 over the sine of pi over x, or cosecant of pi over x. Knowing that the step after that is L'Hopital's rule, where we'll have to differentiate the top and bottom, I think it's smarter to shove the x downstairs, because I would rather differentiate 1 over x than 1 over the sine of pi over x. And it's just the simpler looking expression. So I'm going to rewrite this as a ratio, as a fraction. So this becomes lim x to infinity. I'll leave the sine of pi over x upstairs, and I stick the x downstairs as 1 over x. The kind of general algebra rule here is that a times b is the same as b divided by 1 over a, or a divided by 1 over b. So you have a choice. And my suggestion is to send the simpler guy downstairs because you're going to have to differentiate. So now if I try plugging in, right, this now looks like sine of 0 over 0. Sorry, I've written my rule there. This is now the sine of pi over infinity divided by 1 over infinity, which is 0 over 0, which is an indeterminate ratio. So I can use L'Hopital's rule. And my derivatives here do require a bit of love. The sine of pi over x, to take that derivative, I need the chain rule. That would be the cosine of pi over x times the derivative of pi over x, which is negative pi over x squared. I'm thinking of pi over x as pi times 1 over x, and the derivative of 1 over x is negative 1 over x squared. Downstairs, like we just said, the derivative of 1 over x is negative 1 over x squared. And it is advisable to clean this up algebraically before trying to take the limit again, especially since I have an x squared downstairs in both of those pieces. So this is the cosine of pi over x times negative pi over x squared times negative x squared over 1. And I can cancel the x squareds. The negatives give me a positive, and we get lim x to infinity cosine of pi over x times pi. And this is no longer an indeterminate form. So now, as I send x to infinity, pi over x is still going to 0. So this is the cosine of 0 times pi. And what is the cosine of 0?
1.
1. Good. So this is just pi. All righty. So in this case, the limit as x goes to infinity, x sine pi over x, that comes out to pi. So this is an example where infinity times 0 was neither infinity nor 0, but pi.
So when you're going from a step where you're first differentiating it with L'Hopital's rule, why is the denominator negative?
Oh, the derivative of 1 over x is negative 1 over x squared.
Okay, gotcha.
I'm thinking of it as the power rule, right? It's x to the negative 1. When you differentiate x to the negative 1, you get negative 1 times x to the negative 2, which is negative x squared. That's all.
Okay, that makes sense.
Cool. Cool. All right, so indeterminate products, they're all handled this way, right? You shove one of the pieces downstairs, preferably the simpler one, then verify that you get an indeterminate ratio out of that, and then apply L'Hopital's rule. And if you're lucky, one run of L'Hopital's rule will get you out of an indeterminate ratio, but you may need to do some algebra. If I tried to take the limit here, I would still get 0 over 0. Or at least, yeah, I would still get 0 over 0. So we needed to do this algebra and clean it up like this before taking the limit. So after you apply your L'Hopital's rule, see if there's any algebra you can do to make life better, and then take your limit. Indeterminate differences can be fun too, although these are generally not so bad. Here's a slightly gnarly example. So let's look at the limit as x goes to 1 from the right, 1 over the natural log of x minus 1 over x minus 1. And it's easy to infer here that this is going to be an indeterminate difference because it's a difference. But if this problem showed up outside of section 4.4, you would want to take a second to think about it. So I want to go through this process to check that this really is going to be infinity minus infinity. You may not know what the graph of 1 over ln x looks like, but you should know what the graph of ln x itself looks like. Here it is, right? We've got a vertical asymptote at 0. We approach that going down from the right. The domain is just 0 to infinity. And this x-intercept happens at x equals 1. So as x goes to 1 from the right, ln x goes where?
Negative infinity.
Careful, we're going to 1.
Oh, so zero.
Yeah, it goes to 0. And it's going to 0 in a positive fashion, right? We're coming in this way, not this way. So we're getting out very small positive numbers. So this is the notation for that. The graph of 1 over x minus 1, that whole thing we do know. That's the same as the graph of 1 over x, just shifted to the right 1 unit. So here's the line x equals 1. And here's the graph 1 over x minus 1. So here, as x goes to 1 from the right, 1 over x minus 1 we see is going to positive infinity, right? As I approach this asymptote from the right. So this whole piece is going to positive infinity. And this denominator is going to 0 in a positive fashion. So just kind of plugging things in, lim x to 1 plus 1 over ln x minus 1 over x minus 1, we see this is like 1 over 0 plus minus infinity. And 1 over 0 plus 1 over a small positive number is a large positive number. So this is indeed infinity minus infinity, which is an indeterminate difference. So we do have an indeterminate difference here. And the trick for handling these is to, again, try and turn them into a ratio. And we're lucky here in that we've got some fractions to play with. So sort of the most natural way to take these two fractions, which give us an indeterminate difference, and rewrite it in a way that we'll have one fraction, which gives us an indeterminate ratio, is to have a common denominator, right? Just do sort of the obvious thing. Yeah, exactly. So let's do that. That first piece, so let's say like this, my common denominator will be x minus 1 times the natural log of x. This piece needs to be multiplied by x minus 1. And this piece needs to be multiplied by ln x. So this is what we get. And now as x goes to 1 from the right, this is going to 0 and this is going to 0. So the bottom is like 0 times 0. And the top, if I think about it like this is going to 0 and this is going to 0. So the top is like 0 minus 0. And both of those, 0 minus 0 and 0 times 0, are equal to 0. Nothing indeterminate about the numerator or denominator on its own, but the whole thing is now an indeterminate ratio. So now I can use L'Hopital's rule. The derivative of the top, the derivative of x is 1, the derivative of 1 is 0, so this is 1, and then minus, the derivative of ln x is 1 over x, and downstairs, here I would need a product rule. So the derivative of x minus 1 is 1, so I get 1 times ln x plus, and now I leave the x minus 1 alone and differentiate the ln x, that's x minus 1 times 1 over x. Now, if you send x to 1 in this expression, you get 1 minus 1 over 1, which is 0. And downstairs, you get the natural log of 1, which is 0, times x minus 1, which would be 0 times 1. So this still looks like an indeterminate ratio. And even if you do the natural algebra, which here might be to multiply top and bottom by x, giving me x minus 1 over x ln x plus x minus 1. This will still look like an indeterminate ratio. This still looks like 0 over 0. The top is going to 0, 1 minus 1. This piece is going to 0, 1 times the natural log of 1, which is 1 times 0. And this piece is going to 0. So this still looks like 0 over 0. And we saw an example on Wednesday where even after one run of L'Hopital's rule, you can still have an indeterminate ratio. You just do it again. So I'll run my L'Hopital's rule one more time and see what we get. The derivative of the top is now 1. The derivative of the bottom is a little bit more complicated. X ln x requires a product rule. So that's the derivative of x, which is 1 times ln x, plus x left alone times the derivative of ln x, which is 1 over x.
Excuse me, how did you get the x limit x approach 1 plus x minus 1 over x multiple logarithm x plus x minus 1 parentheses? How did you get that?
Oh, from here to here?
Yes.
I multiplied top and bottom by x. So just to simplify things, just to kind of get rid of the fractions, I noticed there's a 1 over x upstairs and a 1 over x downstairs. And in order to get rid of that, I chose to multiply the top and bottom by x. So when I distribute here, I'll have x minus 1. And when I distribute this x down here, I'll have x ln x. And then x times this piece, the 1 over x cancels, and you just get that. You could also have a common denominator top and bottom, right? I could rewrite this as x minus 1 over x, rewrite this as x ln x plus x minus 1 over x, and then flip and multiply. But multiplying top and bottom by x is much faster. So what I'm doing here is multiply top and bottom by x to simplify. I would rather work with an expression that looks like this than an expression that looks like this. specifically because I know I'm going to be differentiating again. And these ratios, like here, I would need something like a quotient rule. That's not fun. So when we do that, we multiply top and bottom by x, we get here. And then sending x to 1, we see that we're still looking at 0 over 0, which means I'm going to use L'Hopital's rule one more time. The derivative of x minus 1 is 1 minus 0, or just 1. The derivative of x ln x is ln x plus x times 1 over x. That's a product rule. And the derivative of this x minus 1 is also 1. What happens as I send x to 1 now? Well, I'd have 1 over the natural log of 1 plus this piece is 1 times 1 plus 1. The natural log of 1 is 0, so this is 1 over 0 plus 1 plus 1, which is 1/2. So this limit is 1/2. But it requires 2 runs of L'Hopital's rule after doing the algebra to turn it into an indeterminate ratio. Any other questions on this guy? Okay, I'd like to move then to talking about indeterminate powers. Remember that an indeterminate power these are kind of the trickiest of all. These are things like 1 to the infinity, 0 to the 0, or what did we say the last one was? Infinity to the 0. These usually require that we kind of take a step back and rewrite the expression using logarithms in order to turn it into an indeterminate product. And then we work with that indeterminate product algebraically to turn it into an indeterminate ratio. And then we apply L'Hopital's rule. So kind of the strategy use the natural log function to turn the indeterminate power into an indeterminate product. And then use algebra to turn into an indeterminate ratio. Then use L'Hopital's rule. And there's really 2 ways to go about this. And it's a matter of taste which one you prefer. So in order to show you both ways without being confusing about it, I'm going to show you what I like first, and then I'll show you a kind of alternate path if you prefer. This is a classic. And as we send x to infinity, the 1 over x piece here is going to 0. And the x piece up here is going to infinity. So this looks like 1 to the infinity, which is an indeterminate power. So what I'm going to do is I'm going to work with the natural log of 1 plus 1 over x to the x instead. Specifically, I'm going to write f of x equals 1 plus 1 over x to the x, and try to calculate the limit as x goes to infinity of the natural log of f of x. So that would be the limit as x goes to infinity of the natural log of 1 plus 1 over x to the x. And then because of the algebra rules for the logarithm, this is the limit as x goes to infinity of x times the natural log of 1 plus 1 over x, right? So this power can come down here. Remember, the logarithm of a power is that power times the logarithm. If you try to take the limit at this stage, you'll get infinity from the x here times the natural log of 1, which is infinity times 0. So we've managed to turn our power into a product. And the way we handle the indeterminate product, remember, is to take one of these two pieces, either this x or the natural log of 1 plus 1 over x, and shove it downstairs as its reciprocal. And again, my suggestion is to take the simpler guy downstairs. So I would rewrite this as the natural log of 1 plus 1 over x divided by 1 over x. And as x goes to infinity, this is now looking like the natural log of 1 over 0, which is 0 over 0, which is an indeterminate ratio. So we have succeeded in getting to an indeterminate ratio. And the trick was to work with the logarithm of our function instead, right? This is the function I'm trying to take the limit of. And instead of working directly with it, I work with the natural log of it, because that allows me to bring this power down. Once I get to this, I've got an indeterminate product. So I know how to handle that. I take one of these pieces and shove it downstairs as its reciprocal. And that gives me an indeterminate ratio, to which I can finally apply L'Hopital's rule. The derivative of the top is somewhat complicated. Let me do the bottom first. The derivative of 1 over x is negative 1 over x squared. We've used that already today. Who remembers how to differentiate the natural log of some stuff? Right, just think of this as some stuff. How do you differentiate the natural log?
Chain rule.
Yeah.
And then the natural log of x is 1 over x. Or sorry, the derivative of a natural log is 1 over x.
Good. So by the chain rule, if we want to differentiate the natural log of some stuff, that's going to be 1 over that stuff times the derivative of that stuff. So here I'll have 1 over 1 plus 1 over x times the derivative of 1 plus 1 over x. And then the derivative of 1 plus 1 over x, this is not bad. The 1 differentiates to 0, 1 over x differentiates to negative 1 over x squared. So this is lim x to infinity, big fraction. Upstairs I have 1 over 1 plus 1 over x times this guy, which is negative 1 over x squared, divided by negative 1 over x squared. And conveniently, those cancel. So what I get out here is just the contribution from this piece, which is 1 over 1 plus 0, which is 1. But that is not the limit of my function. That's the limit of the natural log of my function. So here's how I would wrap this up. I would say, therefore, the first thing I'm going to write down here might look a little bit weird, so I want you to just watch carefully. The ln of the limit as x goes to infinity of f of x by our rules for limits is the same as the limit as x goes to infinity of the ln of f of x. Right? Remember, one of our rules is that limits can pass in and out of continuous functions. As long as we stay away from 0, the natural log is continuous. So the ln of the limit of f of x is the same as the limit of the ln of f of x. And the limit of the ln of f of x we just discovered is 1. So now if you exponentiate on both sides, you get e raised to the power of the natural log of the limit as x goes to infinity of f of x is equal to e to the 1. But the object on the left here, e raised to the ln of some stuff, is just that stuff. So the limit as x goes to infinity of f of x is e. And that's the limit I wanted, right? i.e. when x to infinity, 1 plus 1 over x to the x is e. And this is the standard definition of the number e. We talked about this a little bit back in section 3.1. Now you see one of the ways to justify that. So if you begin by taking logarithms, then you end by exponentiating, right? Whatever you get out here, you're going to have e to that number. That will be your original limit. I mentioned that this is not the only way to approach this problem. The two ways to approach this problem are isomorphic. They're the same, but the symbols you write down are slightly different. So let me show you one other way. I have known people who prefer this other way, although it's rare. An alternate approach we use the fact that anything is equal to e raised to the natural log of that thing for any positive quantity a. This is a true statement, right? E raised to the natural log of a. The e and the ln's eat each other up. That is the same as a. Usually we look at stuff like this and simplify it to this. But you can also say, okay, I'm going to start with my thing and then just call that e raised to the ln of that thing. And this feels a little bit backwards, but there's a step, no matter which approach you take, there's going to be a step that feels a little fucky. There's no getting around it. Either you can do that step at the end or at the beginning. The first approach I showed you, you kind of do the funky step at the end. Here you do it at the beginning. So I could say lim x to infinity, 1 plus 1 over x to the x. I think the appeal of this is that it's direct. we're going to have an unbroken chain of equal signs with the correct answer at the end. I can say that this is the limit as x goes to infinity of e raised to the power of the natural log of 1 plus 1 over x to the x. So I'm doing the same thing. I'm saying that this thing is e to the ln of itself, right? This. And then we do all of our work up here. This is the limit as x goes to infinity of e raised to the x times the natural log of 1 plus 1 over x, which is, here's kind of an odd step, right? Well, it's up to you. Some people would take this limit and shove it into the exponent here. And technically that's what we're doing. So that's what I'm going to write. Again, I'm using that fact that limits and continuous functions can commute. You can stick a limit into a continuous function or pull a limit out of a continuous function. From here, I do all the same stuff that I did to this piece before. I'm going to recognize that this is an indeterminate product. And rewrite as e raised to the limit x to infinity ln 1 plus 1 over x divided by 1 over x. And you work it from here. So you do some L'Hopital's rule, and you'll get e to the 1. I don't think either approach is very nice. I'll be clear about that, but I prefer the first approach. Your book shows it both ways. And the advantage to doing things this way is that rather than saying, okay, stop, I'm going to go work with the log of this function instead, and then at the end saying, okay, now I'm going to exponentiate, you kind of do everything all at once. You introduce the exponential and the log in one step, and then you just work directly. So you will have an unbroken chain of equal signs that are true, and then your answer at the end. That is kind of nice, but you have to do all the same work. And I think this feels a little weirder, usually, especially to Calc 1 students, but I encourage you to practice them both ways and come up with something you like. This, of course, would be an indeterminate ratio. And so you do your L'Hopital's rule, and the derivative of this is the same as it was before. Everything cancels, you get 1. All right. And the remaining examples, I'll be using the first approach because, like I said, I find that more appealing. So one of the fun functions to play with here is this guy. Yeah, I'll flip back really quickly here. So I'm not showing all the L'Hopital steps here because they're exactly the same as they were with the first approach. It's the same problem. Here we just attack by starting out like this rather than taking the log. Okay. So the function x to the x is interesting. It's weird. It's not an exponential like 2 to the x or e to the x because the base is not a constant. But it's also not a power function. It's not like x squared or x cubed because the power is a variable. So both the base and the variable are powers. This is a weird function. It's not something that you'll see a whole lot, but it makes for a great indeterminate power. Because if you go ahead and plug in 0, you get 0 to the 0. The base being 0 wants to make the whole thing 0. The power being 0 wants to make the whole thing 1. So this is an indeterminate power. So instead of working with f of x equals x to the x, I will work with the natural log of that function instead. So I'd say that the limit as x goes to infinity of the natural log of x to the x is the limit as x goes to infinity of x, I'm sorry, not infinity, 0, 0 plus of x times the natural log of x. And this guy, as you send x to 0 from the right, x itself wants to go to 0. The natural log of x wants to go to negative infinity. So this is a 0 times infinity, which is an indeterminate product. So in order to handle that, I rewrite it, lim x to 0 plus. Again, I'll shove the x downstairs, ln x divided by 1 over x. As x goes to 0 now, this looks like negative infinity over positive infinity, which is an indeterminate ratio. So I am free to apply L'Hopital's rule, giving me lim x to 0 plus. Derivative of ln x is 1 over x. Derivative of 1 over x is negative 1 over x squared. And if I just do some algebra here, this is lim x to 0 plus 1 over x times negative x squared over 1. And the x's cancel. You get lim x to 0 plus of just negative x, which is 0.
So our final answer will be 1.
Good. So the natural log of my function tends to 0. And here's the way I like to write it, yeah? So I wrote things kind of formally in that first example. Here's how I like to write it. I'd say that the ln of f of x goes to 0. Therefore, f of x itself goes to e to the 0, which is 1. And this is as x goes to 0 plus. All right, I think this is easier than writing that full thing where we say the limit of the natural log is the natural log of the limit is the natural log of this, blah, blah, blah.
I have a question for the beginning that 0 multiple minus infinite. The minus infinite is the logarithm x going from the right side of the.
Yeah, that's coming from the graph of the ln. So again, here's the graph of ln x. So as we approach 0 from the right, the natural log function dives down to negative infinity.
Okay,
Will there be
thanks.
cases? Oh, sorry. Will there be cases where what we end up with after we've gone through this whole process will be something more complicated than a single constant that gets put over E? Like, are we gonna end up with like a function that becomes a power of E?
Yeah, it's possible. So here's a fun example problem that I give my Calc 2 students. Because we use this a lot when we're testing series. But only if there are free constants in the thing. So in general, the answer after you do all the L'Hopital work should just be a number. That's our goal, certainly, is to get a number out of these limits. That, or it could be, you know, infinity. That's possible as well. In this case, after you take the natural log, you'll find that this limit is a times b. So the overall limit is e to the ab. And it follows the exact same steps as the first limit, just instead of a 1 for where the a is, there's the constant a. Instead of a 1 out here, there's a b. But in general, you will get a number out of this. So unless the original problem has some free constants, then you should be getting a number out as your answer.
Cool, thank you.
One of the reasons L'Hopital's rule is useful is because we might want to graph a function like x to the x. And if I'm going to try and graph that function, I need to know what it looks like near 0. And this is kind of, well, the limit as x goes to 0 of negative x, yeah, I'm just plugging in, right? The function negative x is continuous at 0. So I really can just plug the 0 in here and I get negative 0, which is 0. From here down to here, what I'm doing is remembering our strategy. So we worked with the natural log of our function instead of the function itself. So what we showed is that the natural log of my function goes to 0, and then I exponentiate on both sides here. So e raised to the power of ln f of x is f of x itself, and e raised to the power of 0 is 1. So I'm kind of sticking both of these in the power of e. In other words, this arrow right here, what I've done is exponentiate. When I exponentiate the object on the left, the natural log goes away. And when I exponentiate the 0, I get e to the 0, which is 1. Correct. Yeah, the final answer here is 1. I suppose I can restate this, i.e. lim x to 0 plus of x to the x is 1. Yeah. There are ways we can modify this, like 2x all to the x, or x raised to the tangent x. Any pair of functions here and here, which both themselves go to 0, would give me an indeterminate power. And there's lots of things like that in your homework, or will be lots of things like that in your little mini homework over the weekend. The real reason we're doing this, though, is to investigate function behavior near strange points, because maybe I want to graph them. So here begins our little intro to section 4.5. Suppose I want to graph y equals x to the x. Well, all the stuff we did in 4.3 is going to be really useful, like finding mins, maxes, concave up, concave down, all of that. I want to do that. But in addition to that, I would like to find things like the y-intercept, which, you know, this guy near 0 is trouble. So I might look at y prime. To even find y prime here, I need to use logarithmic differentiation. So I'd say, all right, the ln of y is the ln of x to the x. So the ln of y is x times the ln of x, which differentiating gives me y prime over y equals ln x plus x times 1 over x, which is ln x plus 1. So y prime would be the ln of x plus 1 times y, which is the ln of x plus 1 times x to the x. This piece, we're looking for critical numbers. Let me take it over here. So y prime is equal to 0 if one of two things is true, either x to the x is 0, or the ln of x plus 1 is equal to 0. This first guy, turns out there's no solutions to this. You can kind of try to think about what solutions to this might look like. The only candidate would be 0 itself, right? If you take a non-zero number and raise it to a non-zero power, you're never going to get 0. And if you try to plug in 0 itself, well, that's the limit we just took. So this guy has no solutions. This guy, on the other hand, has one solution. This is true if and only if the ln of x is -1. And if you exponentiate on both sides, you get x equals e to the -1, or 1 over e. So on my y prime number line, there'd only be one number here. It's 1 over e. And to the left of 1 over e, we could test something. To the right of 1 over e, we can test something. Something we could test to the left of 1 over e would be like 1 over e squared. And something over here we could test like just x equals 1.
I have a question for your right side. That has y prime over y is equal to logarithm x plus, yes. How do you get the y prime over y?
Differentiating this implicitly using the chain rule. So this step right here, this is implicit differentiation. Remember, we said the only way we can find y prime here is using logarithmic differentiation, which was something we talked about back in section 3.8. Logarithmic differentiation is where you take the natural log and then differentiate implicitly on both sides with respect to x. So the derivative ddx of the natural log of y by the chain rule would be 1 over y times y prime, which is y prime over y. Okay. So let's come back here to our y prime, which is this thing. All right. Put it in a little box here. If I plug in 1 over e squared, I'll have the natural log of, I'll write it as e to the -2 plus 1 times e to the -2 raised to e to the -2, which is certainly a scary looking expression, but it's not too scary for us to manage. The natural log of e to the -2 is -2. So this is -2 plus 1 times e to the -2, all raised to e to the -2. I don't care what that is. It's positive. It's a power of e. So this is -1 times a positive number. So this is negative. And to the right, if I test x equals 1, I'll get the natural log of 1 plus 1 times 1 to the 1. The natural log of 1 is 0, so this is 0 plus 1. 1 to the 1 is 1, so this whole apparatus here is 1. In particular, it's positive. So I know that my function is decreasing until we get to 1 over e, and then increasing thereafter. We could also attack it with the second derivative if we wanted. We would again, I believe, need to differentiate logarithmically, which is a little bit intimidating here, but let's do it. So I'll take the ln of y primed is equal to the ln of ln x plus 1 times, let's see, I need some more parentheses here, times x to the x, which is the ln of ln x plus 1 plus the ln of x to the x, which is ln of, let's just write this as ln x plus 1, I don't need that second paren anymore, plus x times the ln of x. So if I were to differentiate this again, I'd get y double prime over y prime equals the derivative over here. This would be 1 over the ln of x plus 1 times the derivative of ln x plus 1, which is 1 over x, plus product rule here, ln x plus x times 1 over x. So I get 1 over x times ln x plus 1 plus ln x plus 1. And then if I want to recover y double prime from this, I would multiply both sides by y primed. So this is going to be 1 over x times the ln of x plus 1 plus ln x plus 1 times y prime, which we know is ln x plus 1 times x to the x. And we're quite lucky here in that some of these scary terms are going to cancel. So leaving the x to the x on the outside, but distributing the ln of x plus 1, I get y prime prime equals 1 over x plus ln x plus 1 all squared times x to the x. And we know that x to the x is always positive. So if I want to work with my second derivative, it's really just this piece. I don't even need to make a number line here. We know that x to the x is always positive. Also, the ln of x plus 1 all squared is positive because it's a square. And we can say even more. The ln of x plus 1 all squared plus 1 over x could never be negative unless x itself were negative. But the domain of my original function is only the positive numbers. So y double prime is always positive because the domain of y equals x to the x is 0 to infinity, and the expression above must be positive if x is positive. You see, the only way for this second derivative expression here to ever be negative, for us to even think it might be negative, is if this piece is somehow making things negative. X to the x is an exponential thing, it's always positive. This is a square, it's always positive. So this is the only piece that even has the potential to switch between positive and negative. If x is greater than 0, this is positive. If x is less than 0, this is negative. But the domain of this function is just 0 to infinity. You can't hope to plug in negative numbers here, at least not any intervals of negative numbers. Because what the hell is negative pi raised to the negative pi? Or negative 1/2 raised to the negative 1/2? Thinking about the domain of this is one of those funny things that I would encourage you to do in your own time. This isn't something I would ask a non-honors class to do, but I don't feel uncomfortable asking you guys to do this. What happens if we try to plug x's which are less than 0 here? Well, -1 is okay, right? You could plug -1 in here. You get -1 raised to the negative first power, which is -1. And negative integers in general are okay here. But if you start trying to plug in any negative fractions or negative irrational numbers, you're going to run into trouble right away. Like -1/2 raised to the power -1/2. I'll give you one example. This would be 1 over the square root of -1/2, which is not a real number. What is it? It's 2 times the square root of 2 times I. So when we're trying to answer the question about concavity, where is this second derivative positive and where is this second derivative negative, you realize pretty quickly that this thing is always positive. The only way it could possibly output a negative number is if you feed in a negative number. But the negative numbers are not a part of the domain. So in other words, my number line for y double prime, I have nothing on it. There are no numbers to plot here because there are no places where this is 0 or undefined, not that are in the domain. So this guy is always positive, so we're always concave up. So we have here our number lines for the first and second derivative. And always concave up. And this tells me that to the left of 1 over e, I'm decreasing. To the right of 1 over e, I'm increasing. And finally, by the previous example, we know that the limit as x approaches 0 from the right of x to the x is 1. So the graph here is kind of interesting. You have your inflection point here, or sorry, not inflection point, you have a min here at 1 over e, and you're always concave up. You go from decreasing to increasing, and your limit as you approach 0 from the right is 1. This is a bit of an extreme example. I just wanted to use an example where we had to make use of an indeterminate power. And believe it or not, this is the simplest of those. Most of the time when I have you guys graphing functions in 4.5, you won't need to deal with indeterminate powers. You'll be using L'Hopital's rule at worst to find things like horizontal asymptotes. We can verify with Desmos if we like. I think maybe before I send you off, yeah, you see over here, you get this weirdness to the left of 0 because we're running into complex numbers all over the place. But over here, we are always concave up, and we have a min at this guy, which is 1 over e. I think it would be nice to show you one not so terrible example before we conclude. So next time, I'm going to run you through all of these steps, right? The guidelines for sketching a curve as presented in the textbook has you doing a whole bunch of stuff. Determine the domain, determine any intercepts, check for symmetries. These can be useful. Is your function even or odd? This is what I mean when pre-calc is coming back. Determine if your function is periodic, right? Sines, cosines, stuff like that. And then you're going to look for asymptotes. This is where we're likely to run into L'Hopital's rule. Right? The majority of problems you'll encounter L'Hopital's rule when you're looking for horizontal asymptotes. Horizontal asymptotes come from limits at infinity or negative infinity. And then all the stuff from 4.3. Right? You're going to find intervals of increase and decrease, mins and maxes, concavities and inflection points. So let's grab one moderate example. Yeah, sure. I'll post this as soon as I can. So the x to the x example is, if anything, an extreme example because the derivatives there are quite unwieldy. But let's see if we can't. Sketch this guy. And what I want to do is find all of the features we've talked about. Intercepts, asymptotes, intervals of increase, decrease, mins, maxes, inflection points, and intervals of concave up and concave down. So first, my domain. That denominator is equal to 0 at x equals plus and minus 1. Right? If I factor the top and the bottom, top there's nothing to do. The bottom factors as x minus 1 times x plus 1. So my domain is everything except for plus and minus 1. Intercepts. This whole thing is equal to 0 if and only if the top is equal to 0, which would mean x is equal to 0. So the x-intercept, there's only one of them, is the point 0, 0, is also the y-intercept. I do have some asymptotes. In pre-calculus, we teach that you find vertical asymptotes by setting the bottom equal to 0. And that's true here as well. But we can also think of it in terms of limits. Y will go to plus or minus infinity as x goes to plus or minus 1. Right? If I send x to 1, then this factor downstairs is going to 0, and I would get 2 over 0, which is infinity. And if I send x to negative 1, this factor is going to 0. So again, I would get something like 2 over 0, which is infinity. So we have two vertical asymptotes. Horizontal asymptotes. Here we would have the opportunity to use L'Hopital's rule if we wanted, I look at the limit as x goes to positive infinity. And in this case, rather than using L'Hopital's rule, I can use some algebra. If I divide top and bottom by x squared, I get 2 over 1 minus 1 over x squared. And that limit is 2 over 1, which is 2. And on the left-hand side, I'll get the same thing as x goes to negative infinity, 2x squared over x squared minus 1. Is again 2 over 1 minus 1 over x squared. And whether you're going to positive infinity or negative infinity, the 1 over x squared goes to 0. So this is 2 over 1, which is 2 as well. So y equals 2 is the horizontal asymptote. And we approach it on both sides as x goes to positive and negative infinity. My first derivative, I can cook up using the quotient rule, would be x squared minus 1 times 2x minus, 4x. 2 times 2x minus 2x squared times the derivative of the bottom, which is 2x, all over x squared minus 1 quantity squared. So this is 4x cubed minus 4x minus 2 times x squared times 2x is another 4x cubed, all over x squared minus 1 squared, which is x minus 1 squared times x plus 1 squared. So this is negative 4x over x minus 1 squared times x plus 1 squared. So if I want to make a number line for my first derivative, the critical numbers for this function would be negative 1 from this factor, 0 from the top, and positive 1 from this factor. Let's see. We are going a bit over time, so after I finish this number line, I'll pause here and we can revisit this on Monday. But I just want to give you an idea for what a typical problem looks like. To the left of negative 1, we could test something like negative 2. The top would be positive, and both of these factors are always positive. As we jump over the negative 1, because he comes from this even multiplicity factor, we would not change sign. As we jump over the 0, he comes from this odd multiplicity factor, so we would change sign. And as I jump over the positive 1, he comes from this multiplicity 2 factor, so I would not change sign. So we are increasing, increasing, decreasing, decreasing, which means I have a local max at x equals 0. All right, I don't want to get in the way of your next class. So I think this is probably a good place for me to stop for today. We'll look at the second derivative of this function on Monday and then finish sketching the curve. I don't want to intimidate you, but this section, section 4.5, does involve an awful lot of stuff. Even a gentle example like this one is a long problem. So I'm not going to include any 4.5 stuff, at least nothing like this, in the little homework set for the weekend. The little homework set between now that I'll release today and have due next Wednesday is just going to be more section 4.4, more L'Hopital rule stuff. And then on Monday, we'll try to complete a few exercises like this, where we're going to go through this whole procedure and come up with a good graph of the curve. All right. Is there anything else we want to say here? I don't think so. No, this is a good place to stop. As good as any. So I will see you guys on Monday when we will talk about curve sketching. Then Wednesday of next week, we will talk about applied optimization. And that will be the last section that's going to be on your test. So next week I will release the study guide, and the following week we will have our second test.
Professor John,
yes.
I will check the video later tonight. If I didn't see any video post, I will send you an email before Monday, because I want to follow the class before next class happened.
Sure.
So yeah, so if you see my emails, it shows I didn't see any video this week. Could you post it again?
Sure. I'd be happy to do it.
Thank you so much.
Alrighty, guys. I'll see you on Monday. Work on the homework sets, and if you get stuck, you can come by office hours, send me a Canvas message, anything like that. Take care.